Bismillah ar-Rahman ar-Rahim. Good afternoon, everyone. Welcome at the new lecture. Today, we will try to solve this question. This question will dealing with another element. This element will be different from the last two lectures because here we will dealing with germanium arsenide, not with silicon, but at the same temperature with room temperature. Here, like we saying here, concentration, donor concentration at the conduction band equals 0. Here, at branch A, a plot that's mean a draw, the same meaning. Draw the position of the Fermi energy level with respect to the intrinsic Fermi energy level, that's mean EFI, is a function of the acceptor. Impurity concentration over the range of concentration, acceptor concentration at the valence band equal or bigger than exponential 14, smaller than or equal exponential 17. Here, intrinsic Fermi level, like I said at the last lecture, will be at the middle in any type, in p-type or in n-type, will be at the same position at the middle between the conduction band and valence band. Here we will facing another difference like the last lecture. Fermi energy level will be at the p-type will be EFP. Fermi energy level in n-type will be EFN, and near from conduction band, far away from valence band. Okay. After complete the solution about A, we will talk about branch B, okay? Now, let's start to solving this question. The expression of the distance between the intrinsic Fermi level and whole Fermi level of p-type. How I know I'm dealing with p-type dot, because ND smaller than NA, that's mean b-type, we're dealing with b-type dots. Here, concentration of holes will be the majority, concentration of electrons and nodes will be the minority. Why? Because we're dealing with p-type dots. Like I said before, we have three important lines: conduction band at the up, at the bottom line is the valence band, at the middle, intrinsic Fermi level. Because we're dealing with p-type, we will draw EFP whole Fermi level, near from valence band, far away from conduction band. Here, let's we will depend on this important equation. Let me use the pencil. Yes, this will be important. We will depend on it. Yes. Intrinsic Fermi level minus whole Fermi level equal KT. T is it is the same, the room temperature. K, the Boltzmann constant. That's mean the last result to these two elements equal .0259 ln P naught, the concentration of hole divided on intrinsic Fermi level. Here, because we're dealing with p-type dot, that's mean from the mass law, P naught here equal acceptor of donor. Okay, at the valence band, we will start by using this result, exponential 14, to find the result about this bracket. Okay, like we know here, at the silicon intrinsic carrier concentration, it was 1.5 dot exponential 10 at room temperature, but here we're dealing with germanium arsenide. That's mean we're dealing with another number. Here, Ni equal 1.8 dot exponential 6 at the same unit. Here, the last number here, 1.177 electron volts. When Na exponential 17, just I will change this place. Okay, I will put 10 exponential 17 instead of exponential 14. That's it. And we will calculate this math equation again. Let me delete these things to can go to other. Okay. Now the last result about intrinsic Fermi level minus whole Fermi level equal 1.356 electron volt. Now let's talk about B. Plot, that's mean draw the position of the Fermi energy level with respect to the valence, here to the valence, not to the intrinsic Fermi level. That's mean all the situation is different. Band energy over the same acceptor impurity concentration as given in part A. We will dealing with same results of acceptor concentration of valence band, exponential 14, exponential 17. Let's complete to solve this B. Plot, draw the position of Fermi energy with respect to the valence band expression for the distance between EF and EV. We will depend on this in this equation. Let me use this figure and this ring, this color, the ring in Turkish language, I'm sorry. KT will be at the same result, ln NV. NV, that's mean the effective density of state, the valence band. And this different from silicon, that's sure, definitely. Here, NV for germanium arsenide at room temperature equals 7 exponential 18 at room temperature. Now, let's start from exponential 14. KT dot 0 to 159, then NV, that's constant at room temperature, but we must calculate it again if the Arthur change the temperature. 7 exponential 18 divided on exponential 14, the last result is 288 electron volts. Now when Na equal exponential 17, just we will rechange this place. We will put exponential 17 instead of exponential 14. Let me delete all of these to can go to the another. Yes. Now let's draw the important 3 lines, the EC conduction band, Fermi energy level at the middle, and EV. Here, let me use that. Here. The EFP whole Fermi level will be near from valence band, and like I said before, why we didn't say why we didn't write EFP minus EFI, because this process be like that. The upper one EFI minus the element below it EFP. Okay, and at n-type will be EFN minus EFI. We must note that very well. Let me delete that and complete. Now we finished this question. Thank you about your time. I will see you in another lecture. Eyvallah. Gelecek derste görüşürüz. Kendinize bakın.